periodic table of the elements is what's called the atomic weight. This is in grams per mole here. So what we find on average for a mole of hydrogen atoms, 6.02 times 10 to the 23rd hydrogen atoms, on average, turns out to weigh 1.00794 roughly, if we want to consider that. But see, it's not an even one. What this results from is that a very small fraction number of hydrogen atoms, remember hydrogen I said was one proton, which we now know is in the middle of an atom, the nucleus they call it, and one little tiny electron, usually envisioned to somehow be in a cloud surrounding this. Well, ever so often what we find is there's a neutron, given the symbol NO. What a neutron turns out to be close enough is the mass of a proton and an electron. And that's why it doesn't turn out to be a 1.0000. And the 794 actually is from a smaller, even smaller percentage of water. It has to have one proton. But what we find is it has two neutrons. Two particles here is why this is called deuterium. And three particles, because the electron hardly weighs. So one proton, two neutrons, three particles roughly, called tritium. Deuterium is another name for the two particle mass. This is known as heavy water. Heavy because on most water molecules, just about 99.99, roughly 9%, are one proton only. And the smaller percentage, bring these decimals in, is having one neutron, and another smaller percentage having two neutrons. Some may even have oxygen. It turns out to have roughly an atomic mass of 15.999, which we'll round off to call 16. Oxygen, 16, we know it has an atomic number of 8, so that must mean there's 8 neutrons on average in any given oxygen molecule. So now in order for a mole of water, what we're going to see is it would be roughly 16 for the oxygen, and then we would need 2 times the 1.0079, call it. So now we would see that 2 times 1 is 2, and this would still be like almost 2. So if we called this 2 plus 16, there would be 18 grams for 1 mole of water. A lot of people don't like the metric system. Look at this. One mole of water is 18 grams. We want to know the volume of that. It's 18 milliliters. So in 55.5 moles of water in 1 liter, we can now determine that 55.5 times 1 mole, Avogadro's number, 6.02, times 10 to the 23rd. That is the total number of water molecules. There's 55 times 6 times 10 to the 23rd water molecules in 1 liter of water. This is our reference point. Now if we remember Mickey and Mimi as grabbing proton ears and back and forth, this proton transfer is what the whole principle of pH is. In our 1 liter of water, the 55.5 moles, a certain number are in the hydronium state. I'll write it H3O plus, because that's the way it's most commonly written, and OH minus. This is H2O with a proton, and this is H2O minus the proton. Out of 55.5 moles, there are, at any given moment, at room temperature, this percentage of a mole. You're going to see when we write this as an exponent, it's not a negative number because it's got a negative exponent. It's still a positive number. We're to the right side of 0. So if we move 1, 2, 3, 4, 5, 6, 7 places, we can rewrite this now. Instead of 0.12345 zeros and a 1, this can now be written, since we moved the decimal place, minus 7 places. 1 times 10 to the minus 7. This is the number. It's not quite 1, so it's a fraction of 1 mole of water that has either taken a proton or lost a proton. In mathematics, there's a way to, instead of even a shorter notation than dealing with these exponents, we can do an operation to this number that's called taking the negative log of it. Can't take the log of a negative number, so we'll take the negative log in order to make this positive. What this turns out to be, written this way, take the negative log of 1 times 10 to the minus 7, the negative and the negative, the log makes just the exponent, is 7. This is a pH of 7. This is considered neutral in water. 7 being the minus 7th of 1 mole is how many protons are available for water in 1 liter. Out of the 55 moles, 1 times 10 to the minus 7 have an extra proton that they took from an adjacent water. So there is an even balancing. This is why a pH of 7 is considered neutral in most biological systems. So, for example, extra protons are considered to be called acids. H2O plus more protons than the balancing number hydroxide, OH minuses, results in an acidic solution. So, if in the